Okay, so today we're going to talk about the Fourier transform for convolution. Fourier transform and discretization. So what we had talked about last time was there's a property of the Fourier transform that if you take the Fourier transform of the product of two functions, then what is it? It is supposed to be the convolution of their Fourier transforms. Or if you take the Fourier transform of the convolution of two functions, then the resulting term is a product of their Fourier transforms. So this is what we're going to start off with. So suppose f, g are functions on the real line with Fourier transforms as following. F hat omega is this. Fourier transform of f and the Fourier transform of g is given by the same kind of formula. So suppose we've got this situation going on. Then what we're going to do is we're going to take a look at Fourier transform of their product. So then Fourier transform of f G is going to be convolution, and I should bump into here and expose the fact that this is a function of omega. And this is going to be the convolution of their Fourier transforms. To put what this is, C, G, omega minus. That's supposed to be it. So that's one thing that's true, and then dually, the other thing that is true is that if I were to start with a convolution, if H is the convolution of f and g, oops, no Fourier transform now, S, G, T minus S, S, so this is H of T, then H hat of omega is then just the product. And notation, we sometimes will write H of x as f star g of. So that star is sometimes used for convolution as well.
You don't need hats in the H and T equation?
Here?
No, above.
Here? This one? No.
Or inside? No.
No. No, this is just defining a function that's in the original variables. So this is the convolution between f and g. And if you take the Fourier transform of their convolution, then it turns into a product of their Fourier transforms. It's dual to the statement here. If I take the product of the two functions, so this is, this is now, what is this function? This is the function which is f times g, or f of x times g of x for all points x. And that's then the convolution of their Fourier transform. So you can write it like this. So it's a little bit subtle. It's kind of nice because when you think about if I have functions, a space of functions on minus infinity, plus infinity, say the L2 functions, it's a vector space. I can add them, subtract them, scale and multiply them. But it also, better than that, it's a ring. I can multiply them pointwise. But there's a different product. That other product is convolution. So you have these two ring structures that you can put on functions. The Fourier transform sort of goes between them in some fashion. Okay, so let's prove this. prove this. So let's see here. We could prove either direction. It really doesn't matter a whole heck of a lot which way we prove it. Let's prove the Fourier transform of the product one. So let's do this one first. So what we show is one part statement. The other follows by duality. So let's pick the first one, and we'll ask for this one. And what is this? Well, just straight up from the definition of the Fourier transform of f times g, that's f of x, g of x. That's the function I'm transforming. And then here's the other part. Okay? Now, this g of x thing, for instance, I can think of that as, well, I can think of that as being something that is, instead of Fourier transform, has been inverse Fourier transformed. So now, let's use the fact that g of x is the inverse Fourier transform, or it is the inverse Fourier transform of its Fourier transform. It sounds worse than it is. And notice no minus sign here. So let's use this formulation. Fg transform is, all right, so let's see, f of x using minus 2 pi I x. Now I'm going to rewrite this g of x in this integral format. I would say I've already got an omega in place, so I'm going to use a z instead. And this whole thing is dx. Okay. So I've just substituted in that for g. Now, as is almost always the case in these kind of situations, the right thing to do is to try to use Fourier's theorem in some fashion or another, try to change order of integration, and in particular try to group up the exponential guys. Because if we can group up the exponential guys, maybe we can turn this thing into a situation where we've got some kind of delta function thing going on, or some. So we change the order of integration. So instead of the x integral being on the outside, the z integral will be on the outside. So repeating. So the z integral is going to be on the outside. G hat of z. And let's say the x integral is going to be on the inside, so this guy here is going to stay on the inside. This guy can't go on into the outside, this factor, because it's got an x in it. This one is going to have to go on the inside, so is that one. And this is going to be e to the 2 pi I. And now I've got an x, but let's see here. I've got an x, in fact, we take out a minus sign, and that's omega minus c. And this is the omega integrals on the inside, the z integrals on the outside. Okay. Did I mess it up?
No.
Got all the minus signs right? I think I do. All right, but now if you look at this, this is the Fourier transform of f, just evaluated instead of omega at omega minus z.
Oh, I think you mean dx.
That should be dx.
Oh, yes. That should be dx, thank you. Is that what you were actually thinking of? No. Okay. Could have just said yes. All right, anyway. So this thing in the square brackets is actually just the Fourier transform of f evaluated at omega minus z. Z. All right, so indeed, I've shown that if you take the Fourier transform of the product, I end up with a convolution of the two Fourier transforms. Now, this is not exactly what I wrote down on the board before, is it? Go look at your notes.
With the G.
Right. Wait. I said F, G should be F hat Z, G hat omega 1 is Z. Easy. Are these things different?
No.
No, why not?
Because it's multiplication, you can just...
What's that?
Because you did multiplication, you just changed the
I've heard two correct proofs, which is great. I heard a change of variables, that certainly does it nicely. And the other one was the observation, this is symmetric in F and G. There's nothing at all different about F and G, so I could have just switched them. So both of those work. Of course, the change of variables, I'd do something like, I don't know, y is equal to omega minus z, and then I pick out the minus sign, fine, and that minus sign flips the order of my integration. It's not really a big deal. Anyway, so either way, this is the same. This is the same. So, end of proof. So convolution and product sort of fit together in this way. Now, how many people have seen convolution before? Some, not everyone. How many people can compute convolutions graphically? Yeah. Let me show you how to do that, because it's very useful to understand what convolution means. Here it's, it's product, okay, fine, and I did something, but what does convolution actually mean in terms of functions on their own? It's very useful to understand this.
Haven't we been doing convolutions this whole time?
What's that?
Haven't we been doing convolutions?
We've been writing down a lot of convolutions, you're right. We have been doing a lot of convolutions, because in particular when we've been dealing with Green's functions, we convolve with a Green's function.
Yeah.
But we haven't really computed a whole heck of a lot with them. So I figured I'd do an example or two to show you that.
Okay.
So let's compute some convolutions. So for example, okay. So here we go. Let's try, and I want to do this practically all graphically. I'd like to avoid writing down any formulas as best I can. Sorry, Mark.
Oh, that's okay.
We could do some formulas too, but I want to show you graphically because it's rather nice. So, I'm going to write down. It's useful to sort of have some scale diagrams for this sort of thing. So I'm going to write, this is going to be x, 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 this is going to be f, this is going to be g, and this is going to be f, convol g. Okay. So what I want to do first of all is show you how to convolve a delta function with some other function. So let's make f be a delta function. Make f be a delta function. Make a little arrow to indicate that there's a delta function there. We'll say this is delta function occurs at x equals a. So as a formula, f of x is equal to deltas of a of x, that distribution. Sort of being a little cavalier with Fourier transform, saying that I can Fourier transform a distribution instead of a function, and that's totally fine in this case. All right. Now, what about g? Let's make g be a function, and I'm not going to write a formula for this guy. I'm just going to draw it. Something like that. This is it's a function. Function supported on an interval b to c. So in particular, g of x is 0 when x is in interval. X is not in the interval. If you will, g is what we call a compactly supported function. Okay, so let's try to compute the convolution. So what does that mean? Well, from the standpoint of the definition of convolution, f star g evaluated at x, it's going to be f of x, g of x, g of x minus t, or by observation of symmetry there, it could be f of x minus t, g of t, dt. Either one of these will give you the same answer. So, well, let's see here. I said f is a delta function. Let's put it in. I'll use this lower form here. Delta function at a, x minus t, g, t, dt. Actually, it's probably the worst one to pick. Let me use the top one. Just for complete clarity, let me just. Delta of t is a, g of x minus t, dt. So what is this? How do I evaluate this integral? Of course, this integral is meant to be evaluated like the distribution this thing is. Where is delta of a? Where does it take its? Where does it pick out the value of everything else in the integral? At a, right? So when t is equal to a, so this thing is going to have what value? This is going to be g of what? This is g of x minus a. So what has it done? What has this convolution done? It's shifted. That's right. It has shifted this function. And how has it shifted? Left, right, up, down? It's shifted to the right by how much? A. Right, so here this is b plus a, and here this is c plus a. So that's what the convolution does when you convolve with a delta function, is it shifts. It shifts by this amount. Now you might ask, okay, so if I were to have a delta function here and a delta function here, where would this new delta function be in its convolution? See, if g were instead of this funny shape, if g were, say, delta at b. Yeah, exactly. That's exactly what it would be. So, convolution with deltas moves stuff around. This is kind of important because what this means is if you're, let's see here, what this means is if you're dealing with something that looks like this now, not in the x domain, if instead I replaced all these x's with omegas, it means that, well, how do I do convolution? How do I convolve to Fourier transforms of functions? What do I do to their original functions? Multiply them, right? So what this means is if you wish to manipulate the frequency domain, the Fourier transform domain, what you end up doing is you multiply the time domain, or in the original domain. This means that it's possible to manipulate the frequencies of signals rather easily. This is what actually happens in the inside of modern radios, and I'm thinking now about what I mean by modern. I mean certainly since the 1930s, modern radios, in which they have what's called the Heterodyne Process, which sounds very fancy because back in the day it was very fancy. Now we realize all it's doing is it's multiplying signals. But what it does is by multiplying signals, it convolves them. That's kind of neat. So let's see here, how does that work? Well, there's a,
Can you say musically what that would mean?
yeah. In fact, last time I showed you musically what it meant, and I can remind you. So let's do it. Let's make sure the phone is not on silent. And let's turn up the volume. And what I'll do is I'm going to load for you two things. Actually, I'm going to write on the board first what I'm going to do and then show it to you. So I'm going to have F be sine of 1,000 pi t, where t is in seconds. G will be sine of 500 pi t. Now, what's F hat? These are t. What's F of omega? What's F of omega? Well, all right, let's, if it's not immediately apparent, let's write out the formula. Sine 1,000 pi t times e to the 2 pi I omega t dt. So let's write sine out as complex exponentials. That's probably easier. This is e to the 1,000 pi t with an I minus e to the 1,000 I pi t over 2i. That's what that is. E to the 2 pi I omega t.
Not a negative 2 pi?
No, it's not. Okay, so let's see here. What is this? This I should split up into two integrals. One that is this guy and one that is this guy. So this is e to the 1,000 pi I t plus 2 pi I omega t over 2 pi t. The other integral is basically the same kind of thing, e to the minus 1,000 pi I t plus 2 pi I omega t dt over 2 pi. Okay. Well, let's see here. What does that look like? What are those? What are those guys? Those are Fourier transforms of complex exponentials with very definite frequencies. So let's see here. Perhaps what I should do is I should group this whole thing up a bit. So this is equal to, we pull 1 over 2i out. This is e to the what? Let's see, I see an I and a pi, and we pull out a 2. 2 pi I, and let's see, both of them have a t, times what? 500 plus omega. Okay, dt. That's the first one. And the second one is minus 1 over 2i e to the just negative. Let's see, right? So 2 pi I t, and let's see, then there's a minus 500 plus omega dt. Now wait a moment. Where have we seen these before? Where have we seen the integral of e to the 2 pi I t omega?
It's delta or
Yeah, those are spectral representations of the delta function. So this is 1 over 2i, delta at what of 500 plus omega? It's delta at 0 of 500 plus omega. Minus 1 over 2i, delta at 0 at minus 500 plus omega. Put another way, if you like, these are delta at 500. Wait, I got this backwards. That's at minus 500. This is plus 500. Omega. So if you will, in that diagram I just had a moment ago, here's omega. So F looks like that. Actually, this height here This height is, well, I'm showing you the magnitude because I've got imaginary stuff. So this is the magnitude of f. Now what's g look like? Without doing computation, I think you can see it.
250.
Yeah, half is wide. So the red one is f, the green one is g. Okay. So now we want to convolve these. So these are now two tones. Now, if I multiply two tones together, what happens? Well, there's a famous trig identity that I am always in the process of getting. Right? So let's say what is h of t, which is f. Well, this is the product like this. And what's that? And look it up in a calculus book or Wikipedia or something or other. Right. It says trig identity. But it's either, let's see, is this the sine one or the sine cosine one?
Jesse would know.
Jesse would know.
Sine, cosine.
Is it the sine cosine one? Let's say it's the sine cosine one. Is perhaps equal to. This is sine of what? 25% chance. Yeah. Well, actually, no, they go together. Sine sines, sine cosines. But let's say for a moment. So this is going to be sine of the sum, 1500 pi t. Plus or minus, again, I don't remember which the sine is. And there's a cosine, right?
That's
No,
cosine,
I got it.
You got it? All right,
Yeah,
read
it's
it off.
1/2
1/2.
times open parentheses.
Yep.
Cosine of 1000 pi t
Uh-huh.
minus 5000 pi t.
500 pi t.
Yeah, sorry, 500 pi t.
All right, so that's 500 pi t. Yep.
And then close that first, yeah, minus cosine, and then you add the two angles.
Perfect, thank you. All right, so this is not perhaps, this is actually equal. All right, so what is that? Well, that's some trig stuff, right? Now these sines and cosines, you see, if I had switched this out for sines and cosines, what would happen? That sign would, if I had said, instead of sine, it said cosine here, it would have put a plus here, plus here, plus here, wouldn't have changed the magnitudes any. So it would still look like this. So what does this look like though? This is a sum of 500 pi t. All right, what's the 500 pi t look like? That's this guy. It's in here. Same right here, but half as high. And then there's also at 1500. At 750, you're absolutely right. So their product in the frequency situation with the omega domain in the Fourier transform looks like these four blue arrows there. Okay, so that's what the trig identity says. Now if I were to convolve the red and green functions, what do I get? Well, let's try to write that out and see. And then once I've got all that unpacked, I'll show you what it sounds like. All right. So let's see here. I've got 1 over 2i omega, or delta rather, of 500 minus 1 over 2i delta at 500. And this is at, let's call this one the omega variable, or the z variable rather, the z. And then what do I do over here? This is going to be convolved with the other one, which is 1 over 2i. And now instead of the 500s, I'm going to have the 250s here. Minus 250. But this is going to be omega minus z. Minus 1 over 2i. And this will be the plus 250. And this is again omega minus z. And then it's d omega. Okay. So that's the convolution of dz. That's a convolution. So let's see what that convolution is.